Assalamualaikum warahmatullahi wabarakatuh. I wish to Professor Zurina. My name is Mohammad Ikhwan bin Muhammad Shafi'i, and today I would like to explain about the Aspen process diagram for our group. So this section will be covered by me, myself, and another person, which is Feng. Okay, for starter, I would like to show the different reactors that we have in our process flow diagram. Okay, for starter, this is primary reformer, RF1. RF2 here is the secondary reformer. HTS and LTS both stand for high and low temperature shift reactors. And the fifth one is the METH, which is methanation reactor. And lastly, it is the NH3R, which stands for the ammonia synthesis reactor. Okay, and then another thing, I want to show about the a number of different streams or feed that are coming into our system. Okay, first of all, it is the feedstock itself, which is the LPG here. Steam, they both are coming into the primary reformer. Next is the raw air, which comes into the air separator. And lastly, we have the most important part, which is H2O. So H2O here functions to absorb the ammonia from the gas stream inside our absorption column. Okay, another thing to mention is the recycle stream that we have in our system. So we have a number of different recycle streams, but I want to show the most important one. So we have from H2GSP here, which is hydrogen gas separator. We recycle the stream from here until mixer one. So that is all from my part. I will pass on to Feng for the further clarification on our design of absorption column. So thank you very much.
Move on to the other sections. The remaining section are carbon dioxide removal sections, the ammonia directions sections, and also the recycling sections. In a carbon dioxide removal section, there are HTS, LTS, and CO as separated. The purpose of the carbon dioxide removal section is to convert as much CO as possible to CO2, since the existence of CO will affect the reaction in the ammonia synthesis reactor. And the chemical reaction in HTS, LTS are H2O plus CO will become H2 plus CO2. And next, after the LTS and after the CO2 separator, and in the methanator, same thing, the chemical reaction here target the CO, since CO have to be reduced as much as possible. But however, in this time, H2 will be spent to react with the CO, is the H2O. And next, we're going to water separator, and then going to the ammonia reactor, and then going to the refrigerator to separate the two phase. The RFG will be going to the absorber, while the liquid phase will be going to the end product mixer. And for our absorber, the outer temperature and outer pressure are negative 10 degrees Celsius and 8 bar. And from a mole flow rate, we can see that for a mole changing, we can see that it is efficient in the aspect of actually NH3. So initially, we have the inlet gas inlet stream, which is NH3 gas RF, which has a NH3 10.7106 kilomole per hour of NH3, and a H2O stream with a 8,000 kilomole per hour of H2O supplied to the absorber. And then, as we can see that for the NH3, the outlet will be having a gas stream and also liquid stream. See, in the absorber, it is the water to wash the remaining ammonia contained in the mixed gas. So we successfully get 10.5806 of NH3 extracted from a total of 10.7106. And the rest are 0.16003 still remain in the gas phase. And then the liquid stream will enter the absorber, enter the dissolver. And for the temperature, it is the temperature. This dissolver is a bit special. It contains the condenser and also the reboiler. And for the temperature of the condenser, working temperature calculations in this case is 121.75, and for the reboiler, the bottom state for reboiler is 128.825. So the temperature, the working temperature shouldn't be quite far from between that two at two conditions. So the outlet temperature for water fat and liquid phase are 1 to 1.7 at 2 bar and 1 to 8.825 degrees Celsius at 2.5 bar. And the mole fraction of NH3 is also quite interesting, since we have extracted from the we have used the dissolver to extract the ammonia in a liquid to become gas again by using air, and we successfully get 10.5 to 82 of the of the gases NH3 from the 10.5506 liquid ammonia, and the rest will be purged, which is 0.0217052 kilomole per hour, and the rest for the gas stream, it will be entering the NH3 GSP, which is the ammonia gas separator, and then combine with and then join the pure liquid stream in the end product mixer. So from the end product, for the end product mixer, the purpose is to combine both stream in different phase, since the ammonia stream exiting from the dissolver is in gas stream, gas phase, while the other one is a liquid phase exiting from the refrigerator. And for the gaseous outlet of the absorber, it will be entering the H2 removal units, which is a pressure absorption H2 removal unit. The purpose is to extract as much H2 as possible to prevent any wastage. And also for the in this unit, we set the we found the data on the website, and then we set the composition, and also the efficiency in separation efficiency. And we get H2. We get and also we have the successfully extracted almost 90%, more than 90% H2, which is 16808.4 from a total of 18676. And the rest 167.6 H2. It will be entering the another recycle stream. For recycle 2 stream, it will straightforwardly going to the ammonia synthesis reactor again. And the other stream, which have a lesser hydrogen, it will be entering the H2 GSP, which is a hydrogen gas separator again to separate the CH4 and also H2, and then being transferred to the secondary former as a recycle stream. So in our system, there are 3 recycle streams. Recycle 1, which is the H2 and CH4 from the hydrogen removal unit to the secondary former. And the secondary recycle stream is the one from the H2 removal unit to the ammonia synthesis reactor. It consists mainly of the hydrogen. And the third one is a recycle 3 from NH3 liquid separator to the NH3 mixer before the outlet is entering the ammonia absorber. For the final ammonia product, and also for the unit that makes the 2 phase of the ammonia stream, we have the ammonia product mixer to at a condition of negative 76.1046 degrees Celsius and negative 1 bar. And for the stream, for the ammonia we get is 3307.65 with a purity of 0.956699, which is above 0.95. So our goal is achieved. So that's all from our group. Thank you for listening.